Professor Jaroslav Kruis from the Czech Technical University, Faculty of Civil Engineering. Jaroslav Kruis is a well-known specialist in numerical simulation of various difficult engineering applications. So we are happy to have him here, and he will speak about the hydro-thermo-mechanical simulation of deep geological repository of radioactive waste. So please take the floor.
So thank you very much. First of all, I would like to thank organizers for a very kind invitation, and it's a pleasure for me to be here after some time. As Peter said, I will talk about hydro-thermo-mechanical simulations, which are somehow connected with geological repositories of radioactive waste, which is topic which we are working in last approximately 10 years. It's common work with my colleagues Tomáš Krejčí and Tomáš Koudelka. We are from the Department of Mechanics, Faculty of Civil Engineering from Czech Technical University, and we closely collaborate with Professor David Mašín from Faculty of Science from Charles University, which works on a hypoplastic model, which we are using as a black box. There is outline of my talk. I guess that you know what is it, deep geological repository. I will say a few words about bentonite. Then I will show you which balance equations are used in connection with problems which we are solving. The balance equations are solved with the help of finite elements, and at the end I will show 3 examples which I think are interesting, and you can see some difficulties which may be interesting also for mathematicians, because there are very complicated tasks. So first, repository means that there is a small facility on the surface, and in the depth 500 meters under the surface, there is a network of tunnels. In these tunnels, there are boreholes where canisters with radioactive waste are located. And it's a problem how to seal these boreholes. At this moment, in many countries, people believe that this is the best way how to store radioactive waste, because in the past, some countries were thinking about storage in the sea or something like this, but now the idea is in the depth 500 meters to store the waste. In fact, we have 2 main possibilities. One, from the main tunnel, you create several boreholes where you put these canisters, and it's called horizontal storage. Here you see the canister. The remaining part of the borehole is filled by bentonite, and we want to study behavior of the bentonite, because it will seal these bores, and it will be important to prove that there will be no leakage. Another system how to store these canisters is vertical system of storage. It means here is a tunnel. The tunnel is in the direction perpendicular to the bore, and in that tunnel there are vertical boreholes where canisters are here. Again, the remaining space is filled with bentonite, and when all these boreholes are occupied by canisters, also that tunnel will be filled by bentonite. So there are several requirements. For example, the requirement is that hydraulic conductivity of material which will be used as a sealing material should be less than 10 to the minus 12 meters per second. If we want to save, or if we want to satisfy a condition that no microbes can migrate through these seals, the swelling pressure should be greater than 2 megapascals. And on the other side, with respect to canisters with the base, the swelling pressure should be less than 10 megapascal. We are talking about engineering barriers, and for these barriers, we are using, or we assume that bentonite powder will be used, or pellets, or blocks. And now, what is a bentonite? Is a special type of swelling clay, which contains that montmorillonite. What is the interesting property of bentonite? That it absorbs water, and it is able to absorb 600% of its weight of the water. And because it absorbs so much water, we can see significant swelling. It means increase of volume. And we have two limit cases. If there is no constraint on bentonite and the bentonite absorbs water, it increases volume to 8 times of the original volume. If, on the other hand, if you constrain bentonite somewhere and then you put water inside, it cannot expand and it develops significant swelling pressure. And this is what this is why bentonite is thought as an ideal material for the sealing. And another very nice property is that in saturated state, the permeability is 10 to the minus 20, which is fine. And I have a notice here that it's a natural material. It's really natural material. It's a clay, and we believe, or it is believed, that a natural material is better than artificially made material like concrete, because we have at this moment, say, 200 years experience with concrete, but we don't know how concrete will behave after 1,000 years or 10,000 years. But clay is natural material, and these properties are simply its properties, and we can use it. We can use them for the sealing in repository. It's porous material, so we need some variables or parameters which are used in connection with porous media. So first is porosity, which is the ratio of volume of pores to total volume. Sometimes void ratio is used, where in the denominator is only volume of solid phase. Degree of saturation is volume of liquid divided by volume of pores. This is written generally for any liquid, but in my presentation everywhere will be subscript W, because we assume that there is water. But in oil engineering, L is simply liquid. Then degree of saturation of gas phase is the ratio of volume of gas to volume of all pores in the system. And we think that we have solid phase, liquid phase, and gaseous phase. And we superpose these three media together in fact. And it means that if we want to know weight of water in unit volume, we should compute porosity, degree of saturation of liquid phase, in our case it's water, and density. Similarly for gas, and here is weight of solid phase, 1 minus n is a volume of solid phase in unit volume. This picture shows interesting property of bentonite. Here is a pore size in micrometer, and here is a distribution of pores. And you see two clear peaks, which means that in a sample of bentonite, you can see a lot of pores with the size less than 0.0 micrometer, and you can see there also a lot of pores with the size, say, 2 or 3 micrometers. So there are two different pores in bentonite, which causes very strange behavior sometimes, and that double porosity must be taken into account because there are many models which are derived for material with a porosity where we assume approximately same voids in some matrix, but in bentonite it's not true because the water can migrate from one level of pores to the larger or in that direction, and it causes severe difficulties. If you are interested, you can find this paper from 2011, where a benchmark was used, and many authors from various institutions were trying to simulate bentonite response. So here, for example, you see deviatoric stress with respect to axial strain. Here is degree of saturation with respect to volumetric strain. This solid thick line is a measurement from laboratory tests, and all remaining lines are results from various models. So you see that this is true stress, and some models simulate or lead to stress which is here. For example, here the degree of saturation is this with respect to volumetric strain, but the model the models predict these saturations. Here is saturation with respect to axial stress strain. Sorry. So you see that it's really very complicated to describe all parameters or properties or variables which you need, because some model gives very nice response in stress, but very poor response in degree of saturation and so on. So it's really very complicated material, and I put also this slide here because we must think that we have species in our material, which we can divide them into grains, water, and air, and then we are talking about phases, which can be liquid, solid, or gaseous. So, for example, water can be in our simulation in liquid phase, or water vapor is a gas phase. So it means that one species or these species can migrate between these phases. So it's also important to check whether we are talking about phases or species. I summarized a few balance equations in order to show you how these equations look like. So we start from general balance equation, which is here. This is material derivative, this is velocity, and this is source. So if we write that equation for mass balance of solid phase, which is expressed here, we obtain that mass balance equation. There is zero on the right hand side because we know that there is no source of solid phase in the model. And everything depends on everything, in fact. So it means porosity is time dependent, density of solid phase is time dependent. That density depends on pressure in solid skeleton, and so on and so on. So this equation is important because we use it for the material derivative of porosity, and in all other mass balance equations, the material derivative of porosity will be substituted by this term. And it means that we reduce one variable from our system of equations. If we want to balance liquid, so it means we have to take porosity, degree of saturation, and density. We are writing it for water, so there should be W. Now there is source term because liquid water can be obtained from vapor. Condensation of vapor will add some liquid water. And here we see another problem which we should deal with. In mass balance of solid skeleton, the time derivative is with respect to solid phase, but liquid phase has generally different velocity. So we should change everything into one phase. And usually the solid phase is the main phase, and all other equations are transformed to the solid phase. It means that I have to rewrite that material derivative, which is connected with the medium describing liquid, to the velocity which is connected with solid phase. And it means that generally the equation is here, where in all equations will be velocity of solid phase. There will be material derivative with respect to the solid phase, and here is relative velocity of alpha phase with respect to solid phase. Well, if we return back to liquid phase, which is here, we obtain, here is now S instead of W. There is term with velocity of solid, and here is relative velocity of water with respect to solid phase. We need, or we prefer this term here because from Darcy law we can substitute some terms instead of this. And again, here will be derivative of porosity with respect to time, which is substituted by this from the solid, from mass balance for solid. There is derivative of density, but density depends on pressure in the grains, and pressure in the grains depend on water pressure, degree of saturation of water, degree of saturation of gas, and gas pressure. So if we put all these terms together, we obtain mass balance for liquid water. And still we are not happy because we would like to remove that term, which is done with the help of Darcy law, which is here. And if we put that constitutive relationship into the previous equation, we finish with mass balance equation for liquid water, where we have unknown pressure in water, unknown pressure in gas. This is velocity of solid phase. There is also temperature, which was not explicitly written in previous slide, but if you manipulate with the constitutive equations, you will see temperature here. And here is again pressure in the water. So this is one equation which is connected with liquid water. It's a tedious work to derive it. Only for your idea, if you write mass balance for water species, you obtain something like this here, which is extremely, there are very many terms, and we should neglect some of them, or we should express, for example, degree of saturation as a function of pressure in the water and pressure in gas. And if we do this, here we substitute something, and that term will be split into these two terms and so on. But I'm showing these equations because if you take all these effects together, you have something very complicated. And all these parameters depend on many other parameters, and the problem is highly nonlinear. So now I'm going to say a few words about finite elements, and in order to make it clear, we will concentrate only on one phase flow in the forming medium. So we need balance of momentum, where here is effective stress and there is water in, it's pressure of water. And we must write an equation for balance of liquid water. So these two equations we are trying to solve. It's coupled because here we will finish with unknown pressure in water, which is PW. It's here. There is effective stress, which depends on strains, and there is velocity of solids, so it's coupled here. And of course, we need boundary conditions. So the whole boundary is split into part where are prescribed displacement and where are prescribed surface friction. Then we take the boundary again and we split it into two parts where we know the pressure in water and the Neumann condition, it means flux of water inside. So the boundary is split two times, once for mechanical problem and once for transport problem. So of course these two parts are not identical generally. And here are Neumann conditions. It means for gamma T and gamma W. Now we simplify the problem once again. So we say that there is no phase change, constant temperature. We don't take into account gas. We believe that density of water is very small, so it can be neglected. So the equation is reduced further into that form. And I'm still not happy because there is pressure in water, there is derivative of displacement with respect to time. It's velocity of the solid phase. But I'm not happy because here is still the term which contains saturation. But saturation depends on pressure and on volumetric change. So if we incorporate this auxiliary relationship here, we finish with equation which is fine because this is unknown, this is unknown, this is unknown, and all other terms are known or they depend on PV and displacement. So we have that equation, and now for brevity, I will denote this as a CP. CPP, the second coefficient will be CPU and so on. So I finish with equation which is more clear, and all these terms are hidden in these coefficients. So we apply or we use approximation and test functions. So weak formulation for mass balance of liquid is here. With this notation, we finish with mass balance after space discretization. P contains nodal water pressure. This is time derivative of water pressure in nodes, and D is a vector of displacement, and it's dot, so it's velocity. Similarly, for mechanical part, this is total stress, effective stress, there is pressure of water. Now the slides are written for linear law between strains and effective stresses, but in our work we use the model which is developed by Professor Mashin from Faculty of Science, and he is computing effective stress from strain. So in our formulation, if we are using his model, that effective stress is a function, is a vector function of components of strains. Weak formulation, there is coupling terms. Here is coupling term because there is for pressure in nodes. And again, with notation, we have that balance of linear momentum. So we put all these terms together. Sometimes different formulation is used. Here we are working in velocities, but here we are working with displacements directly. In both cases, you see that the matrices are not symmetric. In both cases, because we know what is it, CUP and PU. Here, matrix UP contains degree of saturation, and degree of saturation depends on pore pressure, on water pressure, which is unknown. So CUP is nonlinear, and similarly all these other terms. So we have a after space discretization, we have a system of nonlinear ordinary differential equations, which should be solved in time. Sorry, I pushed the button. So let's go back. Probably I pushed something wrong. Thank you. This will be vector Q. This will be matrix K. This will be Q dot or derivative of Q. And for time integration, we use generalized trapezoidal rule. and we finish with system of non-symmetric nonlinear algebraic equations, which should be solved in each time step of our analysis with these matrices which are non-symmetric, which is generally very difficult to solve, and many methods cannot be used. I show you the simple formulation for partially saturated problem with mechanics only, because if I take into account gas and water and temperature, all these expressions will be extremely long, and I think it's not necessary. If you are interested, I can give you some references where to find it, or we can discuss it about it later. And now 3 examples. One example is temperature around repository. This is easy from mathematical point of view, because this is pure heat transfer. This is pure heat transfer, nothing else. It's equation of heat transfer, parabolic equation. What is complicated is geometry, because here you see a main tunnel here, and on that tunnel there are perpendicular tunnels, and here are boreholes where the source of heat is prescribed. It simulates behavior of canisters with the radioactive waste, and we want to compute distribution of temperature. I will show you figures in the cut, which is by vertical plane, and the cut will be here. So there is a main tunnel. Perpendicular to main tunnel is that small tunnel, and there are boreholes with canisters, in fact, parallel with the main corridor. And I will show you maybe later. I don't know whether you see it, but on the wall it's not clearly visible. But here you see really that main corridor, and it's better now. Thanks. So what you see here, it's imagine that small corridor, and there are boreholes with the source of heat, and we cut the model, and we are looking on these boreholes, and we see the temperature at the beginning of analysis. After a while, you see much higher temperature, and this color indicates that you have a tunnel, there is a borehole which generates heat. The heat is flowing under that corridor, and in this cut here under the floor you see some heat flux which is going to the opposite side of that corridor. Here again we probably don't see it well. Here is that small corridor with the sources which are here, and now this means this is that corridor with the borehole here, and now we cut it by such a plane, and we are looking from this side. So here you see the temperature, how the temperature grows, and again you see that some amount of flow, some amount of heat is flowing under the floor to the rock massive here. This was calculated because the question was, what is change of temperature here in the opposite side of the corridor if there is a canister which produces heat? It means that there is that corridor, there is the canister, and question is which temperature will be on opposite side of that corridor. And the result is that the temperature change is less than 2 degrees of centigrade, although the temperature here in the canisters is assumed about 100 degrees of centigrade. But the rock is so large that it's nearly negligible, the effect of temperature here on points which are on the opposite side. And this is cut. If you imagine that small corridor with the boreholes here, and if you cut it by such vertical plane, you see that some amount of heat flows under the corridor and some amount of heat flows above the corridor. But the change in temperature is very small. As I said, it's about 2 degrees of centigrade. This was nothing special. It's only interesting to see whether canisters which are heated up to 100 degrees of centigrade cause some significant or not significant changes in vicinity. This figure looks like nothing special, but these lines are tunnels. There are 30 tunnels. In each tunnel, there are 60 canisters. The length of these tunnels is about 300 meters. And the question is, determine temperature everywhere. So this length is approximately 1.5 kilometers. This is about 1 kilometer. These tunnels are 500 meters under the surface. So from that huge cube, the first 500 meters are removed in order to see these. And after a relatively long time, you see that there is nearly uniform temperature because, as I said, in the tunnel we have 60 canisters and their temperature is 95 degrees of centigrade. So after a while, you see that the temperature is nearly continuous here. This is geothermal gradient because the temperature grows with the depth. And here the problem is that if you want to prescribe really these sources, and if you want to simulate canisters in each tunnels, the mesh is sorry, which one? Control. Thank you. There are 1,200,000 nodes, which means 1,200,000 unknowns because of the heat transfer. Approximately the same number of hexahedral elements. This is problem which I can solve on my desktop by Holmot library, but it requires 7.9 gigabytes of memory. So this is the largest mesh which I'm able to solve on my desktop. On the other hand, if I use conjugate gradients, they start with 380 iterations, and after a while, when the temperature is smooth, more smooth than at the beginning, that number decreases. And finally, the third example is really hydro-mechanical analysis. Details are available in the journal, and it was tested in our underground facility, Josef, which is 50 kilometers out of Prague. There is a heater, this red one. It's a heater which simulates canister with radioactive waste. It was located in borehole. The remaining space was filled by bentonite. Here you have you can see this is the heater, and the bentonite is on that. It was solved as axisymmetric problem. So the green color represents bentonite. Rock is not simulated here, and there are points where sensors were located because there were many sensors, and the aim was to compare numerical simulation with measurement. So after 2 years, the temperature, there is a heater. It was steel cylinder, and it generated heat. So it was not in the model. So you see that close to the heater, the temperature is very high. Then the temperature is decreasing. In selected points where the sensors are available, you see measurement from the sensors. That line or these lines are from numerical simulation. There is a suction after 2 years. In this graph, you can see relative humidity again measured in the sample and simulated by model. And here is a void ratio after 2 years. And here is degree of saturation after 2 years. So it means that several variables were computed. That model was more complicated that I showed you today, but I said expressions are too long and too many notations, so I decided for a simple version to understand how the model is assembled. But here more variables were and quantities were taken into account. And you have seen that the you have seen that the results from simulations were relatively close to measurements obtained in that test. So clearly, we need further development of models for bentonite because it's very complicated, as I described during the talk, and we don't have a robust model which can predict all quantities which are required simultaneously. We can predict very well swelling pressure, but other quantities will be not satisfactory. But we need a reliable model. There is difficulty with non-symmetric nonlinear algebraic equations, which we obtain because sometimes it's difficult to determine whether computation fails due to incorrect solver of equations, or some parameter is out of its range, or what is the reason that the analysis collapsed. There is extremely important point which deals with efficient time integration. Society requires reliability of a repository for tens of thousands years. If you want to simulate such long period, you need efficient time integrator. Of course, that after, I don't know, 1,000 years, it will be in stationary state nearly, so the time step could be very long, but still we will need enormous number of time integration steps, and efficient method is needed. I did not notice uncertainty, but uncertainty is clearly very important. Nobody knows exactly what is 500 meters on the surface. So there are some cracks. The material is definitely not homogeneous. It's more or less isotropic, but it's a questionable. So uncertainties will be needed. But you can imagine that if you compute some simulation with sharp data and with uncertain data, that with uncertain data it's very difficult. And now you have difficult simulation, and although if you take into account uncertainties, it will be together absolutely computationally demanding. So. But it will be included somehow, because all these measurements show that some parameters are given by a range from minimum to maximum value, and you should try both minimum and maximum value in analysis. So it will be also very important topic for future research. And it's everything what I wanted to show and to say, and I would like to thank you for your attention.
So thank you for your interesting talk.